we're going to talk about this new idea, right? So it's actually a pretty small idea. It's a small change from my previous thinking, but it's difficult to describe. So I'm going to spend a lot of time describing it, and it's really difficult to understand the implications of it. So, but I'm really excited about it because it gives you a new way of addressing all these issues we've been dealing with. It's like a new tool in the toolbox, a new sort of twist on it, which seems like it's going to open up a lot of avenues. I haven't figured out those yet. So I'm going to describe the basic idea, and there's going to be a lot of details which are going to be a bit fuzzy, and I won't understand all the implications of it. But I'm still really excited about it. Okay, so that's that. That's just a warning about what is about to cover. So I thought I would start with the review of some of the model building stuff, just to give the basis of how to understand this new twist. And so in this picture here, I show a column. You can think of it as a module in Commodity, but I'm drawing more like a column. I'm drawing layer 3, layer 4, layer 6. This is basically the model we wrote about in the Columns Plus paper. It's I can just leave it at that. The basic idea about modeling that we put out in first columns, but then modified in Columns Plus, is the following. You have, and this may be a little bit different than you've been thinking about it, but this is how I think about it. You've got essentially two inputs to a module. You've got some sensation input and you have a movement input. And the basic idea is you sense, you move, you sense, and you move, and if you keep track of where you're moving, you can build a three-dimensional model of something. That's the basic idea. It seems pretty solid. Almost has to be that way. So we know so many things fit that, so that's it. But exactly how that happens is still questionable and so on. The way we modeled it in the Columns Plus paper, I guess in frameworks too, but is we have two layers of cells. One layer of cells receives sort of the sensory input, and the other layer of cells represent a location, and it receives movement information. So these are the two basic inputs to this column. This is going to represent sort of the location of the object, and this is going to represent sensation, but actually they're going to represent the same thing, because the way we did this is that you ultimately end up with an SDR, a very sparse representation in each of these layers. And in the end, that SDR is unique to the object and to the location on the object. And that's true down here too. It's unique to the object and unique to the location on the object. Just a little aside, if you think about the sequence memory is basically you feed in a series of observations. You use time as a sort of scale of instead of movement, we have time. But the SDRs in the sequence memory are unique to all things in the world. They're basically unique to the sequence name of the melody, and it's also unique to the location in that sequence. So it's a unique representation for this element in this location in this sequence. And that's what these representations here are too, that we did in the Columns paper. We basically say, well, we have an input that represents what we sense, but that's not unique, but we're going to make it unique. We're going to make it sparser using the temporal memory algorithm. And we also have a location that is sort of not unique, like grid cells, but we have a couple of different ways I've talked about of making that unique too. So the basic idea here is you basically have this, you're trying to narrow down your possibilities of where you are in the world. And you have two ways of doing it, and they interact with each other so that your location predicts what you should see next, and what you see next tells you narrows down what you might be looking at, and then that tells you what your location is, and so on. So I put these two little dots here because this is this basic mechanism where you have two SDRs, each can be a union, but each is being driven or narrowed down by a different type of reality of the world. So in this case, we have movement and we have sensation. Those are two separate ground truths, if you will. And by using those two different elements, you can narrow down and get to a unique representation of the input in this object at this location. And you can argue that, okay, this is a representation of location that's unique to the object, but that's also unique since they both represent unique locations in the object. That's the fundamental premise. And then we did one more thing in those papers. We proposed that there would be a pooling layer, a temporal pooling layer, where you could take these unique SDRs in a unique meaning, each one is classifiable. Like each one of those SDRs could, if it was a sequence memory, any one of these SDRs would be, you could classify as this is that sequence, right? Because they're unique to that sequence. When you hear, you can say this is unique to some object. And so you basically do a pooling between all these very sparse SDRs onto some stable representation. So it's a many-to-one mapping. And that, that is a representation of the object that you're sensing at different locations. The reason we know this occurs because we have stable perceptions of things. And so there has to be a stable representation. Even though your eyes are moving, your fingers moving, there's a stable representation in addition to that, which is like, hey, this thing is still there, it's not moving. The world seems stable. And so that means there are cells that are stable. And we said this is going to happen in every column. So you can then say, okay, well, we have two representations here. One is stable and it's independent of the sense location. And the other is changing with each movement. And we're only generally aware of this one. We're not able to notice our eyes moving and things like that, generally. We then said one more thing in that paper. We said, hey, look, if other columns are doing the same thing, but sensing different locations, then they're also going to have a stable representation in their column, and we can associate that stable representation with the stable representation. So you have these two very sparse, and if we learn to associate them together, then during inference, they too will narrow down. So there's three narrowing down processes here. The one that's voting between these stable representations, and two that, well, I guess this is another narrowing down, but there's three SDRs that are essentially being narrowed down in different ways. So this is like saying, okay, I'm narrowing down my possibilities by what my neighbors are telling me, what other parts of the brain are telling me, and I'm narrowing it down through sensing and movement. Are there any questions about that yet? That should be all like review, but it takes a while to sink in for everybody. So, all right. There's another twist to this. And we talked about it. We didn't write about this. We didn't know about it at the time we wrote the Columns Plus paper, or maybe, I don't know if we did or not, but there's some other issues here that have to be dealt with. The fact that one is that in our current thinking, there's these models have an orientation. You can think about like vertical north. We talked about that, right? And they can be tilted. Your head can be tilted, and all of a sudden now you have to compensate for that. And the other thing is that these models have, they were learned at some scale. Now you might be recognizing the object at a different scale. So what we proposed, we never wrote up, but we talked about this a bunch of times. And I think there's a lot of truth to this, is that the brain has to compensate for both scale and orientation. And we're just talking about vertical orientation now, nothing else. And the thalamus seems to be has the right architecture to do both of those things. And it turns out this movement information and the sense information both go through the thalamus before they get to the brain, before they get to the cortex. And there's a very profuse projection from the cortical column back to the thalamus where this is going through. And so we have this theory that says, first of all, the thalamus looks like a multiplexer. It looks like you've got a bunch of wires coming in and they can reroute them to different wires coming out. It doesn't look like it's doing other types of things. It looks like it's doing that, very unique. So we have a hypothesis that it can compensate for vertical orientation. I gave examples of this. Remember when I was talking about like you just tilt your head, which you do all the time, and it's just magically everything seems to work, right? Even though you've actually skewed everything in your brain, coming in on the retina. Yet the movements are adjusted and your perception is adjusted. It's all taken care of. And one could argue that, someone wants a picture of this? Yeah, I'm fine. You're good. So I'm going with this hypothesis now. There's a lot of evidence to suggest this, that the thalamus does both of these. The scale is because there's this frequency, that's oscillation frequency between these two elements here, and that changing that frequency would change the scale of movements and change this. And so I'm not going to go into that, but that seems to be what's going on there. So I just throw that in here because it's going to be important. So we got this model, and we're trying to narrow down what it is. We do movement sense, movement sense, movement sense. We narrow it down by alternating between those two limiting possibilities, and we can do it also by voting. It's not necessary, but it makes things quicker. And underneath it is an assumption that the system has to also figure out the scale and orientation of what the current presentation versus the model as it was learned. I'm ignoring displacements for now. I think displacements can be added on top of this, with this whole discussion today without problem. And so I'm not going to talk about displacements. I'm just going to stick with the model we had in columns and columns plus. All right. It's really important we all sort of on board with this before I go to the next one. All right.
Wait, okay, I've
Good, thank you.
two small questions.
Please, thank you.
There's no arrow going back from the layer 2-3 neurons to layer 4 neurons.
Oh, right. Yes. So it's complicated. The classic anatomy does not show that this projection is going back. And I don't remember if we saw some more recent papers that do say it. In the columns paper, we assumed there was a connection going back.
I think we found some slight support for it, but it's not a.
But we do know,
it's not a
really,
well documented.
we do know there's a profuse connection from layer 2-3 down to layer 5, and so there is this feedback, and it's going to be more complex. And I don't understand it, and so it's a good point, Ben. There will be, if this information does flow back into lower parts, the lower layers of the cortex. It just doesn't go back to layer 4. Maybe Sumita says there's a slight evidence for it. But there is a very strong connection between layer 3 and layer 5. So it does feed back, but in a complex way. Okay.
Let me post these things to Slack real fast.
I'm gonna wait.
If you don't mind.
I don't mind. I'm trying to stick to sort of high level concepts here because the new idea is pretty simple at a high level.
Yeah, I think people need to understand this before they understand what you wrote in the document. Yeah.
So I think I think you agree with it. It's worth going over this again and again because even if it helps me to see it again and again, but it really takes a while to sink in. What's going on there?
Okay, I have one more kind of basic question, but I just need kind of a brief review. In the pooling step, can I think of that as sort of like a sum or a union?
Well, I don't know what those words mean. Sounds good.
Like I have a bunch of SDRs in layer 4 and they're different at different points in time during the sequence. Can I think of layer 3 as like the union of those?
Yeah, well, it's not the union. No, it's not the union of them. The union.
Well, it's a.
Yeah, go ahead.
Yeah, it's a single SDR that's going to be stable, but the synapses on each cell of that form a union of the temporal memory representations. So so if you have all of the different unique representations in layer 4, a single cell has to be able to recognize all of those and stay stable during that. At least that's how we implemented it. So it's a union in the synapses, but it's not a union at the level of the layer 2-3 representation.
Right. I'll just try to show that visually. That's nicely described. You've got an SDR up here. It's very sparse. In fact, sparse is good. And this does not change as you experience more parts of the object. And so you're taking this SDR and you're forming synapses on these cells to this pattern. And then you take the next SDR and you form more synapses on these cells to this pattern and so on. So it's basically mapping many SDRs to one SDR. There is a limit to how much you can store this way. Because in theory, you could be want to store a lot of these things on here, and so there's so many synapses and so on. But this does not get more. This does not become a union of these. It's literally if I put this input in, I should get this SDR. If I put this input in, I should get this SDR. And if I did have a backward projection, this SDR would associate with all of these, but. That doesn't appear to occur directly here.
Yeah, thank you.
So many to one.
The clarification
makes
total sense now.
Yeah, it just doesn't change as you train more. Yeah.
I have a question about the thalamus function.
Yeah.
So it's the idea is so the thalamus corrects all the rotation, and then since at the beginning, let's say we don't know exactly what the rotation of the object is, and so there would be sort of a mismatch until then there's a feedback to the thalamus to say, okay, correct your rotation until it matches.
Yeah, we've never worked out the details of that, Heiko.
Mm-hmm.
So but yes, it has to infer that information. And but in the same way, it has to infer everything. So there's going to be some sort of process to do that, to narrow down and say, okay, what is the right orientation and what is the right scale? But we've never worked out the details of that.
Okay.
But it looks like the thalamus is capable of doing those things. So, and there's this very large projection from the cortical column back to the thalamus, meaning many, many axons. And there's many synapses. So it's a classic sort of associative memory looking type of thing. Somehow the cortex is that column is going to work with the thalamus to figure out the right answer, just like it's working between other layers to figure out the right answer. So that would be a good exercise to go work out the details of that. But we haven't done that.
Okay, thanks.
Yeah. But you'll see why I think it's important in a moment. Okay, any other questions about them?
So this is just the first layer of the hierarchy, first level of the hierarchy.
This is just one region,
layer that
one
has
column,
sensory input.
just one column in a primary sensory region. Right.
Just make sure, like,
Yeah.
because the output for the other layer is different.
Well, let's go. So now that's a good segue to number 3 here, where we're going to talk about 2 columns that are hierarchically arranged. And so I've labeled those R1 and R2, region 1, region 2, something like that. Now, I've had an assumption for a long time that I think is wrong. And the assumption was, well, we know that layer 3 in R1 projects to layer 4 in R2. That's a well-established fact. I didn't show here, R2 also gets input from the eyes or the skin or whatever, but I can put that aside for the moment. But we do know there's this, it's very clear that layer 3 here projects to layer 4. And so you say, oh, well, that's the input to this guy, right? You've learned something here. Now the object becomes the input to this model. So we're now instead of passing in raw sensory data, we're passing in some processed object that we already recognize, and that being sent to here. So that's why I wrote here, assumed that R1 to R2 was stable SDR, the object recognized. I don't know if I wrote, oh, I just erased something. I think it all erased. An object recognized by R1. So this idea was like, okay, if I recognized, a letter here, then I'd be passing that letter into this guy, and this was stable over movements of R1. The anatomy suggests that's what it is because we got this layer 3 to layer 4 projection. And I always thought that was the way. That was the whole idea of the hierarchical temporal memory was like, oh, we're gonna do these temporal pooling and then temporal pooling and temporal pooling. So you get more and more stability go up. I think that's wrong. There are a lot of problems with that. And I was thinking about the logo on the coffee cup problem and many other problems we've discussed about distortions of objects, and we've talked about how you can lay displacements on top of a morphology and all these things that were just really puzzling. And the basic problem was, if you just say, I'm going to pass this stable representation of whatever I've learned here as an input to this, oh gosh, I wish I just, how did this get erased? Did I do that? Used to tell
I think the eraser, which is right there, slid.
Did you take a picture before?
Actually, the picture is with the eraser half obscuring it.
What? Oh, it slid down by itself?
Or it slid down one way or another.
I don't remember moving it.
I don't know
It's got a mind of its own.
Sliding was.
That's really
But
interesting.
it slid.
Maybe I bumped into it or something. I mean, how do I need to alter what to predict? Fails. I'll say with multiple comes.
Oh no, the picture is missing.
Doesn't solve many. I don't know what I wrote there. I know what
It might be cases curved and arced.
Yeah, angled logo, curved and arc. Many cases. You're right. Thank you.
Yeah.
There we go. Puzzle.
Sneak in and get a fresh picture.
Yeah, that's amazing. I did that somehow. I can't imagine how he did it, but I somebody did it. Okay, here's the thing I was struggling with this. I imagine that R2 is getting this input and says, okay, I recognize this letter A and now it's part of a word or something like that. But all the different R1 columns, remember there could be multiple R1 columns. Each one has its own little space absorbing this thing at different places. And each one's going to have the same stable output, but they're going to have different representations here. And so when I get this, if I'm in this R2 region, I get this input, and I want to send this feedback back to R1 to tell them what to expect. I don't know how to send anything back. I've lost my location information here. It's like I can't say, oh, you're supposed to expect this and your column's supposed to expect that. Every time I tried to work out how this would work, I got totally lost. I can never make it work. It doesn't solve these other problems which we just talked about, where we have these many cases where we had the logo at an angle, the logo at different scales, the logo could be curved around the cup, the logo could be in an arc. There's all these examples that you come up with where I had a model here, and I'm trying to apply it to a parent object here, but none of it worked because everything was distorted. I can't just take this logo in its normal form and just plop it on this. It just didn't work. And so this is where we have this idea of taking the displacements and wrapping around the morphology or something else. So the very simple solution to this problem is the following. It's really kind of simple. Just don't assume, no longer assume that what you're passing here is a stable representation to the higher level. And by the way, I said layer 3 projects to layer 4, but remember, there are a lot of different cell layers in layer 2 and layer 3. Some people have identified at least 4 different types of cells in here. So just because someone says layer 3 projects to layer 4, it doesn't mean there aren't layer 3 cells and layer 2 cells that are not the stable representation, right? It's a simplification. So the basic idea here is R1 does not want to send that stable temporal pool representation. It wants to send its unique SDR right now. It's like, here's what I'm sensing right now. It's like, here's the instantiation of what part of the model I'm seeing in my model. So if I'm looking at the logo here, I would say I'm looking at this letter in the logo. But it's really a unique SDR for it's this location in my model. When it's passed to here, this guy has no idea what it means, right? There's no letters or anything being passed. It's just an SDR. So it's some really sparse pattern that comes in here, and this guy says, well, someone told me that at this location in my model, there's this very sparse pattern that represents what's being sensed by this guy. And so I can then associate this unique location here with the unique location here. If you think about the unique location here, it's like a node. And now I'm associating some pattern with that node. It turns out that there happens to be a node in this model, but this guy doesn't know that. It just says, okay, there's something coming in that's unique SDR. I'm going to associate with my location. And therefore, and that's associating you both ways. And these are connected both ways. So when I get to this location, I can invoke that same unique SDR back over here just by associating limiting. And so when this guy's moving around, let's say it's the coffee cup on the logo, when this guy's moving around the coffee cup, it can tell this guy, it says at this location, this particular, you should be, you should be seeing this very specific pattern right now. I'm telling you what you should be, not only if I can invoke the right pattern here, it's both the location and the object. It's saying like you should be at this point on this object. And you know what to expect from a sensory input. I don't know what that means. This guy says, I don't know what that means, but you should be at that point in your model.
So just so I understand there, so R2 is going to tell R1 what location to predict. And then R1 is the one that knows the details of that particular logo.
It's the unique location. It's the location
that's the unique location.
You're right.
Yeah.
Right. It's essentially this state. The state that's in these, it doesn't really matter. Whatever the state is here, these are both unique to the object and location. And it's basically saying, yeah, given where I am right now, when we went through this, let's say it was a logo, when we trained earlier, when I was at this location, you passed the pattern, and I might now say, oh, that pattern's an N. Let's just hand wavy. And so I said, that was a pattern. I'm going to associate that. So then I'll tell you when I get back here, I'll tell you what that is again. I'll tell you, well, that's what you said it was. That's what you were doing when I was here. And suddenly this guy can say, well, I'm here. You can use that information to narrow down any models we have over here. It's like, I'm seeing this part of this logo right now. And you can use that to narrow down where you think you are on this, whatever model you're making. It's just another one of these SDR to SDR narrowing capabilities, but now we're going between, instead of between two columns at the same level, we're going between two columns at different levels, and we're making the assumption that they're representing different spaces. This is one model of one object, this is a model of another object. And we're doing the same thing. We're just passing this information both ways. We associatively learn it. So whatever I think I'm seeing here, I can invoke all the places you might have seen the logo over here. And if I'm at any place that had the logo, like on the cup that had the logo, and there was an N at that location, I'll tell you that you should be expecting that over here. And these can both be unions. Like if there's uncertainty, if I'm not sure exactly what I'm seeing, and I'm not certain exactly what I'm seeing, they can, again, narrow each other down. It's just one more example of the same mechanism of narrowing down between unions, but this is now doing it hierarchically.
But it's narrowed down the stable representation or the,
No, the stable representation is not being passed between these. It's narrowing down the point here.
the L4 and 6.
It's basically saying, it's helping these guys resolve their, well, I could narrow this down too. You're right, Louis. I'm not being more specific. All I'm saying is literally what happens, the cells that project from the upper region to the lower region, I didn't show it here. I didn't mention it here. They come from layer 6 and they project up into layer 1. And they essentially, cells in layer 5, layer 3, and layer 2 all have their apical dendrites in layer 1. So in essence, the upper region could be enforcing, basically suggesting to all these cells simultaneously, this is the state you should be in. So it's going to be more complex. There might be multiple things going on here. So, but basically, so it could be narrowing down the stable representation. I didn't make that distinction. I'm just saying there is remember I said the implications are complex, so it's a complex. But basically I'm saying I'm using a unique location here. I'm pushing it back here to help you guys figure out where you are. But it's unique. It's not just like, oh, it's a logo. That's not sufficient. I need to invoke the specific state right here. This is the part of the logo you should be seeing, because when I'm at this point in the cup, that's the part I saw. That's what you told me you were seeing. So I'm going to tell you to see that again. Something like that. There's one more twist on this. So I said here, R1 to R2 is not the stable SDR, but represents the mutation on the child. So those are parent-child things. To get this to work, to solve the problems we know we have to solve, you have to also share the orientation and the scale, because the orientation of the logo and the scale of the logo can be changed independently to the orientation and the scale of the cup. I can have a little logo, I can put it at different angles. So that has to be part of what's recalled here. But we're doing it on a point-by-point basis. Meaning, again, imagine if the logo was in an arc over here, it was like, and then it was in a curve. Well, the model of the logo doesn't look like that. But the cup can say, well, at this point, you told me you had an N at this angle, and then you have a U at this angle, and then an M at this, this kind of thing, because that's what this guy would be seeing. It may not even know that it's recognized the entire logo yet, but it basically says, I'm seeing, this U, and it may be part of the logo. So a little hand wave there. the point is that to get this to work, you have to share the orientation and the scale between these two guys as well. You have to say, well, I saw this pattern. I was looking at this pattern, this orientation scale. He says, okay, I'll remember that. And then he says, okay, well, at that point, I'm going to tell you, you should see that pattern at this orientation and this scale. Maybe you could figure this out. Maybe it doesn't have to be passed. I don't know. But the cleanest implementation would be like that. And the question then is, well, is this possible? Are these kind of patterns sent back and forth? Well, there are multiple cellular layers that go between regions like this. And I have to go back and review the literature. We've read it many times, but I haven't looked at it in a few years. The Alex Thompson papers were the best a few years ago. I'm going to look at them again because I want to go very, very carefully through what kind of projections between these two guys. So maybe we don't have to send this, maybe it's inferred, but I think in the general rule, if you want to send this, you still have to send something about the orientation. Well, I don't know if you do it. I could try to figure it out, right? You could just say, you should be still looking at the N on the logo. And it has to say, well, okay, if I'm looking at the N of the logo, maybe I have to figure out the orientation scale on my own. So I'll put this as a question mark.
Doesn't it go to the thalamus as well?
No. Well, not in this direction, no.
Backwards.
Yeah, not in this direction. There is, again, complications. There are these layer 5 cells, which this is typically layer 6. So there's a layer 5 cells here. These are the motor output cells. They also go into the next region, but they go through the thalamus over here. So those are the ones that are considered like motors. So this is like the movement. It's like the movement command is going back to the thalamus and gets modified again, right? It's like
It goes up and back.
yeah, it's complicated. As I said, it's really complex. The idea is very simple. The idea is I'm not sending a stable representation between R1 and R2. I'm sending the unique representation between R1 and R2, and that solves that looks like it will solve all the weird things we could do with child relationships on parents. It can solve curves and arcs and roundedness, and it could even, any kind of weird thing I can think of. It's because we're basically not trying to learn the whole logo at once. We're just trying to say, hey, I saw this thing, which is part of the logo at this location. So, all right. And then later on, you say, well, the logo looks like it's tilted at this point or whatever. And I'll associate that.
This means that this means that R2 has to see every single location on the cup that the logo is on.
But that's not acceptable. So I wrote about this and then and I said, we can't expect that. So there will be a solution to this. For example, I don't know the solution, but I have some ideas. So
why can't R1 just send the location in its reference frame, but the details of what's actually.
Well, that's what it is sending.
No, it is sending. What I mean is that R2 just has to understand the relative location and orientation of the two reference frames. That's just one quantity.
Yeah, but that only works. That works if the logo is not deformed in any way.
No, it still works. Even a deformed logo has a reference frame, so you still have location.
The reference frame will change, right? So
yeah, but that's R1's job. That's R1's job is to represent that. R2 just has to say, okay, where on this object are you at this point in time? And that way it doesn't need to learn that all that really intricate mapping for every single compositional object.
I think that to work, Subutai. So I think that's not going to work. But I could be wrong. Here's what I wrote. It'll work. Imagine I had instead of a cup, I just have this flat surface. And I'm putting the logo at some location and at some scale and some orientation. Well, in that case, all I have to do is learn one point. If I associate one point, then everything else follows, because now basically I can just tell, this guy can tell, you know what, here's a point where I'll give you your orientation, your scale, and your object. And from now on, you can calculate everything on your own, right? So I don't need to store all these points. I can store one or a few, doesn't really matter. But I think when you start having the logo do weird things like the arc, I don't know how that works. Maybe you see it. It seems to me like there isn't, I can't tell you what the orientation of the logo is because at any point in time, it's these weird things are going on with it. There isn't a way of assigning the entire logo to this new space here. I can't do that.
I mean, that space still has some relative orientation and scale with respect to the cup. It may be different from the original logo, but it has something.
Well,
It's still a single association.
But I'm not learning a new model of the logo here. So if I'm not learning a new model of the logo, I'm using my old one. How is it that I'm able to?
But even here, it would have to learn it because R2 has to learn all of those new locations now that correspond to the curved momentous. It's still, in both cases, it has to learn it in a very detailed level.
Well, at one extreme, we don't have to, all we're doing is associating some part of the logo with some here, some part of the logo with some here, some part of the logo here, some part of the logo here, some part of here. And from this guy's perspective, he doesn't know what the logo is. He doesn't know that it has a current, he doesn't know anything about it really. And, but it's just saying, these are the things you told me when I was here, you call them R1, this is what you told me you were seeing. I don't know how you can solve the basic thrust of what I'm thinking here, Subatai, is that I don't see how you can assign the entire logo in these deformed states. It feels like you have to be able to deal with the fact that I'm going to have to map parts of the logo to different orientations.
No, I agree. I agree with that. I'm just wondering, now you have even more learning to do here because for every object that curved logo could be a part of, you have to learn all of these detailed associations.
So,
whereas if you just have to learn about the curved logo once, now you can apply to any hierarchical composition. Now you have this n squared problem of every object it could be in. Now I put the curved logo on a t-shirt. Now I have to go and learn all of those associations all over again.
Right. So I think there's a solution to this, and I kind of hinted at it. Well, I didn't hint at it. I tried to describe it in some level of detail in the write-up, which is the following. If you don't, first of all, if you did learn every location, remember I was talking about the circle. Let me just give you the example there. And I was saying, okay, what are you going to learn a circle? Well, how many points do you have to sample going to the circle? And there's really no salient points. So what I was arguing that I believe these SDR properties, as you move in some direction on any object, the SDRs represent the locations change slowly. And at some point, they change completely. So imagine from here to here, there's a slow changing SDR, and now all the bits have changed. And imagine it's here and again, I say, okay, move slowly, and now all the bits have changed. You move slowly, and now all the bits have changed. This is true for both the location and the sense features and so on. Well, it can change rapidly, but in general, they change slowly. My point was that if I want to learn all the points along here, I don't need to sample all the points along here. That is, any point between these 2 points will correctly be represented anyway. As long as I don't go too far, as long as I go like, okay, this is an SDR, this is an SDR, and this is an SDR, but in between them, there's some shared bits, so they haven't changed completely. Then all the points in here, if I learn this SDR and this SDR, all the points in here are also learned simultaneously. That is, if you point anywhere here, you'll get the correct SDR. It's just like you don't have to sample everything. And if I did sample, if I train myself on this circle by looking at different points and learning the curvature, if you will, if I at some point you have some amount of memory dedicated to that, and then if you sample more points, you're not going to get any more memory. It's just not going to form any more. It doesn't need any more information. All the information is already captured in that. In fact, you can infer it from new locations you never learned it on, as long as you're relying on this sort of continuous SDR property. And I think to me, that's going to be the solution to this. That is, I take like a temporal memory layer here, or any one of these layers. If I have a continuously changing location, and I have sort of a changing, imagine the circle, I have a gradually changing curvature that I can learn the curve without sampling every point, and yet every point will look like I learned it. Every point will be correct, even though I don't have to sample it, and so that it's limited amount of memory you have to store. You don't have to store the unique SDR for each location, because as you go around here, you're only adding a few more bits to different neurons as you go. So it's not like I have to store an SDR here, an SDR here, and an SDR here. It's just, it'll naturally just fill in the spaces in between. So I'm working on that hypothesis that that's the way this is going to get resolved. It's also interesting to point out that, as I said earlier, there are some situations where you can actually capture it all at once. Right? You can say, oh, well, if it's just the logo at some orientation scale, one point will do it, and that'll be good. And you can, and R1 can infer in between. So if all we have is 1 point, R1 will guess in between and say, okay, I'm going to use my model. But then, but if previously it was learned in the context of the cup, then R2 say, no, at this point, you really have a different orientation, different scale, or, that's what it should be. So I realize there's a memory problem here, but I think there's a way around it. And also, another example I gave was, let's say the logo goes horizontally, that's really easy to learn, and then it starts going vertically. Well, clearly you have to learn something about the logo changing at this point. I mean, you just can't use the old model of the logo. This angle could be anything. I could learn it. It's really simple to learn. So it seems like an infinite number of permutations on this idea that say like, okay, I can't just rely on the learned model of the logo. That's not going to work. I have to have someone else telling me this guy saying, you know what, it's not, at this point you should see this, at this point you should see this, at this point you should see this. So the example of this is just that you have to learn something new when you see something new like this. And you have to learn something new when you see something new like this. There's no way you can do this without memory. So you have to do it. The question is how much memory is it going to take, and how's it going to be done? So do you have an alternate solution to this, Susan? I didn't understand what you said, so.
I think I was thinking you do need to learn these continuous representations of the circle and the curve thing and the angle one, but I was thinking R1 would learn it, not R2.
Well, that would be,
it's like a new object or a variation of an object. The reason is that, say we have a new curved logo. We just, Christy decides our logo is going to be curved now.
yeah.
Now I can say, oh, I'm going to put it on our letterhead on a notepad, and I can instantly imagine what the curved logo would look like on the letterpad. I don't need to learn all of those detailed associations.
Yeah.
And I can put it on a t-shirt. I can put it on, different types of coffee cups. I can put it on our door. So all of those can be learned instantly, or I can represent it and predict and reason about it instantly without learning all of these detailed pairwise things between R2 and R1.
I agree. In fact, I would learn that, I think, right? I think I would say, oh, there's a new version of the logo, just like there's a new version of the coffee cup.
Yeah.
But there's many examples where that doesn't make sense. If I put the logo on a flag, for example, I can't learn all the undulation models of the logo. I might have the morphology of the flag represented in R2, which at any point in time could be, folded, whatever. But R1 can't learn, oh, now the logo's folded this way, now the logo's folded that way. Another example would be just the curvature on the cup. When I learn the logo going around the cup, I actually don't learn a new logo. I don't think of it as, oh, there's this logo now going in 3D, right? Now we have this three-dimensional curved logo. I don't even perceive it that way. It's just like the regular logo on the cup. So I would say that, I would argue that's the case where you actually didn't learn a new logo curved on the cup. Because you don't perceive it that way. You think it's the same old logo, it just happens to be wrapping around the cup. So maybe there's two different examples there. One is you've got these sort of morphings of the logo that are not permanent. They're somehow just like fitting to the form of the secondary object. And then there's other things like the arc, where you're making, I would learn that. And I guess I would agree with you, I could learn that. But the other example, I don't think I would learn. The other example, I just have to deal with it.
Yeah, I'll have to think about that. Yeah.
Yeah, as I said, the implications are complex. Yeah, that's it. It's a simple idea. Don't send up the stable pattern. Send up the changing unique SDRs. That's what's going on between level 1 and level 2. There is again the unions narrowing down. So it's another union narrowing down process. In hindsight, it almost seems obvious to me that something like this has to happen, and I gave the reasons why I was fooled thinking otherwise earlier.
Does it also send up the stable pattern?
I don't know.
Or
Well, certainly,
does it need to
certainly,
classify it? Or
if R1 and R2 were both recognized in the same cup in some sense, then it would make sense. I don't know what R2 would do with the stable pattern. I don't know. It's a good question. I don't
maybe
have a
that's
reason
an
for it.
orthogonal thing. If it's
Yeah, it
if
is.
it needs to vote, if it needs to vote on it, then you would need
Yeah,
it.
well, it can't vote on it if R1 and R2 are modeling two different things at once. Right, then there's no voting, right? If R1 and R2 are both modeling the same thing for some reason, like, they're both just looking at the coffee cup, the morphology of the coffee cup, and they're both trying to guess it.
So it is the same thing?
Is that?
Is it the same thing?
Well, I give you
Because there are
the
different layers of the hierarchy. They probably have different views of the same thing, not exactly the same.
well, in this case, I'm arguing that R1 and R2 are invoking two different models. R2 is invoking the model of the cylinder, and R1 is invoking the model of the logo. They're not the same thing at this point. At this point, R1 doesn't know anything about the cup, doesn't know anything about the cylinder. It's just looking at the details of the logo. It says, oh, I see that. It's a logo. Where R2 is looking at a larger picture, and it's not. Now we're going to get into a little weird area here. The question is, I think there's still two different representations. Remember, I said I'm going to ignore displacements for now. I think it's possible that you still each model has a morphology model and a which is really just it's learned by basically learned by the contours of the object, and then it can have a specific features, if you will, at points on that, at points on the morphology. And so where am I getting with that? It's like at this point I was just assuming that R2 is just looking at the morphology, and it's just saying, okay, I'm reading the morphology of the cup, and now I'm at some location on the cup, and by the way, I can associate with this one feature over here. And I'm assuming this guy is I don't know, they're just modeling two different things. And so in this case, it's hard. Its question is, could a column in this regard, you might argue that a column just starts by modeling morphology and then assigns whatever pattern it gets from somebody else. So in the primary region, it's going to learn a morphology of something, and then it's going to say, okay, that's sort of like the shape of the thing, the outline of the thing, and now there's some sensory input that I'm associated with some point on that morphology. So that might be the color of something, or the the shape of the edge, or something like that. I don't know. Again, it's very confusing to me. But I'm going to try to. And my next step here is to try to figure out how to bring back in the idea of displacements and morphology, and build the whole model. It's like here's your graph, here's your morphology model, and then at any point here we can assign some observed feature to that point.
I have a question regarding the back projection from R2 to R1.
Yes.
Is it the SDR of the part, or also the SDR of part and its location?
Well, it's both, right? Those SDRs in layer 4 and layer 6, they're unique to the location and the object.
Yeah, so unique to the location. I'm wondering, does it require the the actual location information itself, because these are two different reference frames.
Well,
You could say, I make a prediction at this location, I expect this part. And I know in your language, this is the SDR for that part. So I sent that information to R1.
Right. The part is synonymous with the location. You can't separate out the two. Remember I was arguing here that both the layer 4 and layer 6, you think, oh, this is the location and this is the feature. But when you actually get down to the SDR is unique to the location and the object, and the SDR is unique to the location and the object.
Right.
Just,
But it's the SDR part and location in the R1 language, R1 reference
in this
frame.
case, I'm just talking about R1 here, yes.
Yeah. So what I sent back from R2 to R1 is actually encoding the location in R1, in the R1 reference frame.
It's basically sending back, in essence, this SDR. And it says, you should invoke whatever you need to invoke based on this SDR. So,
yeah, it's the same kind of SDR that R1 sent to R2, right? The same coding.
it's just returning it.
It's the same one, yeah. It's the same
Yeah.
one.
Okay.
Yeah, I mean, there's a unique SDR here, and there's a unique SDR here. And this says, I'm passing you this, and says, okay, I'm going to associate your unique SDR with my location, with my unique SDR. And you can associate your unique SDR with, I'm going to bias you. I'm going to basically say, you should probably be biased to the same SDR you had before. It's still a simple associative link between two very sparse representations.
Okay, yeah, so it's not the exact same SDR, it's just there's a one-to-one mapping between
Yeah.
the
That's a
arrow
great
this way
point.
and an arrow this way.
That's
Yeah.
a great point, because I think people get confused about that. On the voting here, the voting between columns, the SDR in this column and the SDR in this column are not the same, right? They're not. They're just different SDRs, but you associate them.
Mhm.
Just like here, this is a different SDR than this SDR, but you associate them. So that's the important point here. This mechanism never assumes there's the same SDR anywhere. It just, it can't be. There's no way for the cells to know that. So it's just saying, I've got a unique SDR, you've got a unique SDR. Literally, all we're doing is saying, okay, I'm gonna give you a pattern which will help you narrow down your pattern, and I'm gonna give you a pattern to help you down your pattern. That's the same thing that's happening here, and that's the same thing that's happening here.
Okay.
Heiko, when we were talking earlier, I think this is a lot more data than I had originally assumed. So it's every location along that object in R1 there's an SDR associated with that's sent to R2. So it's a very intricate mapping between these two.
Yeah, I honestly, and sometimes I was with you on this. Initially, I said, this can't be right. But the more I thought about it, I couldn't see a way out of it. It's like, this has to work somehow this way. So then I started thinking about, well, what mechanisms would let it work this way? Now, I could be wrong about that, right? I could totally be wrong. But my thought process is said, I kind of cornered myself to say, to handle all these cases of objects on objects, and all the different weirdnesses about it, I had to come to this idea that there's this very intricate mapping between these two regions.
I think that 3D curved logo was a good example, because we haven't learned that 3D curved logo individually. It's just a flat logo to us, but it's wrapped around the cup.
Yeah.
And that we can have to associate that somehow. Yeah.
The way I think about that is like this. I'm looking at this cup. And of course, I can only see part of the logo right now. And so some columns like looking at part of the logo, and it says, oh, okay, well, I recognize that. This is, because I recognize this part of the logo. I can't see the rest of it. I don't need to see the rest of it. I just, I can recognize it by these local displacements. And so great. I'll just say that, it's like I'm looking at an obscured logo. I say, yeah, I only see part of it, but I identified it uniquely. Then I rotate it a little bit, and now I see a different part of the logo. And that same column will say, yeah, I recognize the logo now. I see these displacements here. The rest of it's obscure. I can't see it. It's okay, but I still recognize it, or I recognize part. I have a good guess it's a logo because it says Memento or it says ENTA, whatever. Where are we going with this? My point was this: is that the curvature issue. I don't recognize the entire logo at once on the curvature. I don't have to. I just have to be able to recognize a part of the model And therefore, the rest of it I can't even see. I can't assume. But I still narrow down and say, okay, I think I'm on the logo on this little section here. And so that's what this column in R1 knows at this time. And so the challenge of wrapping around the cylinder is avoided. I only have to place it right now on this surface of the cup right now. I don't have to worry about where it is over here. I'm not sensing it over there. I'm just sensing this part. It's right there. And then I rotate it again. Oh, it's right there. So as far as the R1 column is, it's just like it's looking at like an included part of the logo. It's like, okay, that's it. And I'll just, and the curvature is irrelevant to me. I don't see it in some sense. So it solves the problem by just because you don't see the whole thing at once, the column just sees a little bit and assumes it's tangential to the cup, and that's all it needs to know at that point in time. And the entire curvature is encoded in R2. R1 doesn't know that. But I agree with you. I think we would learn art logos if I saw them. So that's a good distinction. There are some changes to the logo, which I would learn very rapidly.
Yeah,
When you guys
I've
finish
got,
this piece of the discussion, there's some kind of a request for my own understanding I want to go through afterwards.
I'll let you do it right now.
I'm going to let Heiko continue on this flow here.
it's just a question here. So so R2 represents the SDR for logo part in its reference frame, right? The reference frame of the curved surface of the cup, for example.
Well, no, be careful, Heiko. Be careful.
Yeah.
R2 does not know anything about the logo.
It just knows the SDRs, right?
It just says there's an SDR I'm associating with this location.
Yeah. Okay. Yeah.
Right. That's it. It knows.
Yeah.
nothing
It doesn't.
about
Yeah,
logo.
I agree. Yeah. It doesn't know the logo, but it has the corresponding SDRs of the logo.
It just says, yeah, some SDR. I don't know what it means.
Yeah.
I got it.
Yeah. Right. It's the corresponding SDR on the logo, and it's in its own reference frame. And so I'm wondering, is this R2? Is this separate from another model that would learn the cup?
Well, is R2, I guess I was using the word cylinder. If I just assume R2 is learning the morphology of the cup, well then the morphology could include a handle. So right. I'm not sure what your question was suggesting that there's a cylinder in the cup. And I'm going to keep going the path that there's a morphology model.
Okay.
And then there's associated with the morphology model are specific SDRs that represent the output of somebody else.
Mm-hmm.
And so I guess there would be, if the cup is defined by the morphology of the cup, then I would say R2 is it. There's no other place, that's what it's handling. There's no cylinder and then a cylinder with a handle. Maybe I could learn that, but I wasn't assuming that here. I was assuming a continuous morphology of this thing.
So you're thinking that R2 could also learn the cup itself, recognize the cup?
Well, I'm assuming it's learning the morphology of the cup in this case.
Mm-hmm.
Okay, I have
Ben.
a pretty basic question that I think will kind of just help concretize my understanding. So I just want to go back to what you said about the circle, and you have SDRs at different points on the circle. So, and then there was something going on about interpolating. So I have an SDR associated with this point on the circle. I have an SDR associated with another one. And let's say I now land on a point that's between the two that I've never seen. Just walk me through what happens.
Okay. Just imagine you've got a dendrite. Can I erase some of this? I'll erase it. I kind of wrote this up. Here's a section of dendrite. And I have some SDR I want to memorize. So I'll form 20 synapses, let's say. And that's going to represent some SDR. Let's say it's a location SDR. Okay. Now it's coming out of this thing down here or something like that. I want to recognize it. As I start moving, so I'm at some location in the world, and as the thing starts moving, what's going to happen is some of these bits are going to go away and some new ones are going to appear, right? just because that's what's going to happen. That's the way there's like a bump. It's like a bump of activity, and you're moving the bump in some direction. Well, some new things are added to the bump, and some things fall off the bump. It's always a set of cells that are active, right? In a grid cell, there's a bump of activity. So there's a whole bunch of cells here that are active, and as you move a little bit, and many of them are still active, but a few new ones, and if you go away, and a few new ones are added, right? It's interesting to think about this, by the way, because this bump can move in many different directions. And if the bump moves in one direction, some bits fall off. The bump moves in another direction, other bits fall off. And so essentially, if there were 20 synapses here, and sometimes there's 20 dimensions you can move in, 20 directions you can move in. But just assume that we're moving. And at some point, I'm adding new ones, and I'm forgetting old ones. Okay. So at some point here, I've now replaced the last of the old ones, and I have all new ones. Does that make sense so far? You're looking puzzled.
Yeah. Okay. So these are dendritic segments.
This is one dendritic segment. These are synapses.
Yes. Okay.
And so there's an SDR up here that's representing location, and there's, let's say, 200 bits are active ones, and as I move, and anyway, this dendrite's going to do, it's going to form 20 synapses. Subsample this thing, right? So okay, I'll subsample this. I'll get 20 synapses. That's good enough to recognize a 200-bit pattern. This is the fundamental SDR method. See what they did. So this is a robust representation of that pattern. If I see these 20 bits active, I know I'm at that pattern. Now, as the location changes, these bits come and go, and therefore some of my synapses will become inactive, but I'll be able to form new ones because some new cells become active up here. The point is, as you move the location bump, if you move it smoothly, these bits will change smoothly. That you don't change them all at once. If I jump from here to here, I could change them all at once, but if I move smoothly, they'll be changing one at a time or so, and which ones change first depends on which way you're moving.
Okay, so as I change the SDR that's up here, so really what's happening, there's a cascade of things. There's my location in space, say of my sensor. As I move my sensor, the SDR here representing that location, it's going to change. And all those synapses are already, they've already formed synapses onto that dendritic segment. But as I change, set of synapses that are active change smoothly with the SDR.
Well, then I can form new synapses because I have new bits of some of these bits are no longer active. So some of these synapses won't be getting any input, but there'll be new bits up here that are active. And so I have the opportunity for forming new synapses.
Okay, but that's on a slower time scale. My question is at inference time, basically. I know the morphology of some object, but now I'm sensing a point that I've never touched on.
I'm getting there.
Okay.
Right. So now I have two sets of 20 synapses here and 20 synapses here. These are, now my argument is the following. Imagine this represents a point in space, and this represents a point in space. Anywhere in between here, between this point and this point, I will recognize that. I will infer it because it'll be some of these bits and some of these bits. In fact, what I argue is if I just form these 20 and then I just form these 20, it'll automatically infer in between. As long as these 2 points are not too far away, it'll recognize any pattern in between these two equally. It's actually inferring. It just says this represents the entire span from here to here. This dendrite will pick up anywhere along this span.
I see.
So in fact, this dendrite can't tell the difference between this point and this point.
Right, so this dendrite simply turns on.
It just says it gets an NMDA spike. Now you got to remember, there's a lot of neurons here. This is just one neuron, right? So there's going to be other neurons that are doing the same thing, and the population. Imagine like it's like the spatial, the temporal memory. So you got some of the mini columns are active as you move. So I have two inputs coming in. I have like the sensory input and I have the location input. As they move, the mini columns are going to be changing too. So a single neuron will not represent all points. Right? At some point, this neuron gets turned off and another neuron comes on. It's because this mini column is no longer valid. And so this guy will run some amount of distance across here. So imagine you're looking at the actual output of the temporal memory layer. Some cells are active. As these two inputs change, the location, the sensory change, if you go smoothly through space, the active cells here will change smoothly too. And in some sense, you can then represent, you'll have an SDR that represents all points in between these 2 points here. I need to work it out in a visual example somehow. It's a little weird. I know it's strange. My only point is, if you don't sample too far apart, then all the cells will likely spawn over a range of inputs, but collectively they'll still be unique. And I don't need to learn or train on all the in-between points. And at any point in time, I can come back and have some pattern. If it's one of these in-between points, it'll just recognize it correctly. So I don't need to train at every point, and I can infer on new points. And my example, yeah, I'm sorry, Vivian. Yes, go ahead.
Does this only work with spatial interpolation, where we know how movement correspond to the changes in the representation? So you said there are like essentially like 20 dimensions in which we could be moving, and if you have 2 overlapping SDRs, there are many possible ways how you could interpolate them. So does this only work if I know that it's like a sliding window?
Well, I'm a little confused by your comment. First of all, it only works as I've described it here if the SDRs are changing gradually. Or if they're changing suddenly, there's an overlap, right? So if I sense from one location, I jump to some other location, then I can't interpolate in between them. So it requires smoothly changing inputs. And if the inputs aren't smoothly changing, then it takes more memory. You can still learn it, but it takes more memory. So that's one thing. It doesn't just apply to spatial things. It doesn't apply to just movement things. It's just a property of SDRs. So if the SDR is changing smoothly, like I gave the example, let's say my SDR represented the curvature at some point here. Well, as I move around here, the curvature will change slowly. It'll change gradually. If I got to some point here and all of a sudden there was like a bump out like this, it's a coronavirus, then I get to this point, this SDR would change suddenly and it would take more memory. I wouldn't be able to interpolate at that point, but that makes sense. You have to have more memory to recognize this change. And then it would be smoothly getting along here.
We stopped here.
So it's a general property. I think it doesn't have to just do with locations. It doesn't have to do with movement. But I found it very interesting if I am representing location, that the idea that how this SDR changes between 2 points is determined by which direction you're moving.
My question is this basically kind of the brain's way of doing spline interpolation? So if it's basically asking how many points do I, okay, so I'm sorry, this is going to be a little bit more than
I know.
the idea is how many points do I need to fully specify a function? If the function is pretty smoothly varying or even linear, then I only need 1 point or a few points. And the function here is exactly the morphology of the object.
Yeah.
Then if I'm trying to learn a really complicated function with lots of wiggles in it, I need a large number of
I
points.
think that's right. Although I don't think you can represent, with a spline, I might be able to say, oh, here's one function that represents the entire circle or something like that, right? Or in this case, you still have to learn a bunch of points. I think it's a good analogy.
Okay, so
I
then
understand it.
actually, okay. The next question would be, as I make small changes to where I'm sensing on this object, the SDR that's produced in, say, layer 6, that's going to be either the same as it was if I'm slightly over, or it's going to be different because a couple neurons fall off and a couple neurons come on.
Well, as you move, if you're able to detect the movement, if it's discernible, then something has to change. So some of the bits will fall off. If the movement is small enough that none of the bits change, well, then you can't learn it, right?
So now I just want to walk through what happens if I make that small change and a new SDR happens in layer 6 of R2. How does that percolate back and affect R1?
Well, if R2 is, if you're moving smoothly along the surface of the cylinder, it's going to be changing continuously here, right? Here's a conjecture. I'm making a conjecture. It's not proven. I'm making a conjecture. My conjecture is whenever you have two SDRs that are associating with each other, if they're smoothly changing, it's much more efficient in memory usage than you think. And if they're not changing smoothly, then you have to store something more. So here, if I'm moving smoothly here and I'm moving smoothly over here, then it shouldn't take a ton of memory to do that. It's a general property of associating two SDRs. If they're both changing smoothly, I haven't worked this out. This is my conjecture that needs to be proven, that if they're both changing smoothly, then the memory storage is fairly efficient. It's not zero, but it's efficient enough. There are, by the way, there are a ton of synapses between R2 and R1 in the brain. So there are a lot of memory there. In fact, people have argued there's more memory up in, the storage up in this, these apical dendrites. It's huge. I know it's huge. So there is a lot of memory, but we can't have it. We can't train on it at every point. I mean, that's just not possible. So, or if I do train at every point, if I trace my finger around here, and sometimes I'm training at every point, I can't create a huge amount of memory. So my point is, if I do this, I'll store the same amount of memory if I go like this. Anyway, so that's a general property of, I'm arguing it's conjecture, there's a general property between SDRs. If they're both smoothly changing, then it doesn't take a lot of memory, and the confluence of those two is also a smoothly changing.
So if I'm thinking of R1 is now representing, let's say we are in layer 4 of R1, and now I've got an SDR associated with the description with like a feature on that logo, like the U in Numenta.
Yeah.
So I make this, this is a simple exercise, but it's worth going over it. And so I change the position of my sensor a little bit in R2. This changes the SDR in layer 6 in R2. So now I come back to R1, and I've now got the different stuff biasing my dendrites. So now I'm going to have the same, what you just described. Some neurons are going to fall off, some neurons are going to come online. And instead of the U at Numenta, now I'm getting possibly the M or something smoothly interpolating between the two.
Yeah, I'm moving across from the U to the M to the whatever. So is there a question in that, or is it?
I just wanted to walk through and understand that loop.
I think that was right. You have a continually changing representation of your location here, and you have a continually changing of your representation of your location here, as long as you're moving smoothly. By the way, this may not be smoothly changing if the sense feature changes dramatically. Imagine I'm going from, well, I gave the example like here, right? Where I have a curvature, it's smoothly, and then bingo, it's something completely different. Well, in some sense, imagine the feature is not smoothly changing anymore. It's not that's like it's all of a sudden goes bing. Well, then if I'm detecting curvature or tangentialness or something, well then there's a 90-degree turn here and it's sharp. So that means that the representation over here would change sharply at that point, or here, kind of.
It seems
whatever
like
it
it's
is.
be able to handle many cases, because it could be that the actual morphology changes smoothly, but say the color on the object changes radically at one point.
Right. It is multiple dimensions. I agree. So the point is, obviously, the more unique things that are happening, the more memory it's going to take to handle it. If you want to learn it exactly, because when we learn a lot of objects, we don't learn them infinitely well. We don't learn all the details. Often our concepts are very fuzzy. Only when you study something very carefully do you actually learn exactly what it looks like. You saw that with Heiko's examples of when he was trying to draw things.
Yeah.
I do that with bicycles. I thought a lot about bicycles. I can draw a pretty accurate picture of a bicycle. Most people can't. But you have to really learn all the details, like what does it do here? How does it turn there? Where does this come out? This is horizontal, that's vertical, that kind of stuff. So my point is, we don't we don't necessarily form all these synapses, even though if we're scanning over an object moving around like this, I may not form all the synapses. You know, it's just not, we don't do it. We don't learn all the details. But I can if I really work at it. I can learn more details. I can learn the exact things, how they change and curve and so on. So that's another variable on this. We don't have to store every little thing here. It just, even if I scan over the whole thing. But I could if I really focus on it and I train myself and I pay a lot of attention, like go around really carefully, I can learn all the details. But often we don't. Anyway, the point is that we're getting at is if things are smoothly changing, then it doesn't take a lot of memory. But if things change sharply, like the feature changes sharply, color or the direction, then it's going to take more memory at that point to learn that. It's logical that you have to. Right? You can't learn a detail without learning something.
Can I go through one quick example just to understand
Please.
the interpolation? So if we have smooth changing of the SDR, but we take away the assumption that it's 10 adjacent neurons. But let's say you have 10 neurons that are active in the beginning, then you turn off one randomly and turn on another random neuron in the 100 possible neurons. And then a next step on the circle, you turn off another random one and turn on another random one.
Why would it be random? I guess the random part I'm objecting to.
Well, it would always be the same ones, but it would just not be adjacent neurons.
Well, okay, I don't know what even adjacent neurons mean. It's just an SDR, right? So
yeah, so in the drawing that you have there, you know which one will be the one that gets dropped off, and you know which one will be the one that gets turned on.
Okay, so careful here. I was showing the bump of activity like in grid cells, but if I'm thinking about the location representation here, I'm working under the assumption that this SDR is not this set of bump of activity here. Remember, it's like this would be like the mini-coms that are active, and then there's individual cells in the mini-coms. So at one level, I can say, oh yes, these mini-coms they have meaning, and one mini-com will become active, and the next one come off, and the next one, they are ordered. But when you actually look at the actual, if I have a unique SDR where I'm individual cells in the mini-com, then there is no order. You can't see the order anymore. It's totally lost. It's just like some 100 bits that just happen to exist out in space, and you have no idea that what the relationship to each other is. So yeah, okay.
I guess my question is, if you don't see that relationship anymore, how can you do the interpolation? So let's say I have 10 that are always on, and I have 2 points, and 4 of them are still overlapping, but 6 changed, and now I want to have the middle point. How do I know which of the 3 from the beginning I need to take away and which 3 need to be added, if I don't know how the changes are in the surrounding?
I'm sorry. But some of them disappeared and some of them new ones appeared, right?
Yeah. So how do I know which ones disappeared and which ones got added?
Well, I don't know. I guess I'm confused by your question, because if I have 2 SDRs and they overlap, it's obvious which ones disappeared and which ones became active, right? The ones that are active are added.
You know it from the start to the end point. Those are the 2 points that are given, but how do you know it for a point in the middle, in between?
Well, okay, so here's the thing that was a bit surprising that came up a number of years ago, was that maybe this is related to your question, Vivian. I don't know. This is a valid point, and this is a valid point, right? What about in between? Couldn't this be invalid? Couldn't this set of bits be actually something else? It's like I'm mixing and matching 2 things. You know, we call that a mix and match error. Like couldn't this be an incorrect assumption that these are in between? Theoretically, that's true, but practically it doesn't happen. Mathematically, it doesn't happen. Maybe Subta could explain that better, but that was the insight. It's like, well, couldn't this be wrong? I'm taking half the bits from here and half the bits from there. Well, couldn't there be another point in space that's like that, that's not in between these 2? theoretically, yes, but practically, no. Mathematically, it's extremely unlikely. So I'm not sure, maybe that's getting to your question. How it is that I can be certain that this set here is actually in between this point and this point?
Yeah, I
So-
guess it would be, how do I know which half of the points from the first one and which half of the points from the other one I would
I
take?
don't need to know that. All I need to know that these set of synapses are active and these set of synapses are active. I don't need to know which is from which. It's just a bunch of synapses. The dendrite doesn't know anything about what these represent or which was. It's just saying that if I did this exercise, then the dendrite will recognize every point in between these 2 points and not get confused. The dendrite doesn't know which points come from where and where. It has no idea. There's a bunch of
Okay.
bits.
So the SDR is subsample from a bigger, I think the confusion is the subsample part. The SDR is subsample from the bigger SDR there, from the bigger activation. It's not the whole activation.
It's true. I'm not sure if that's ridiculous.
I think she was saying that's a simulated information from one point to the other, but it's not. It's like a subsample from that.
It is a subsample, but yeah, I'm not sure if that was not. Maybe I don't know. Maybe are we getting close to your question or not?
Yeah, I guess so could you say that this only works for recognizing a new pattern in between, but it couldn't give you a definite pattern in between? So like if I get
I can't predict.
Okay, then it
I
makes
can't
sense.
predict it. Yes, if that's your question, I cannot predict this. I don't. All I'm doing is I'm saying I recognize this.
Okay, that makes a lot of sense. Thanks a lot.
Yeah, there's no prediction going on there. As far as the dendrite is concerned, these synapses can all be mixed together. They as long as they're within 40 microns of each other, you know, the group I'm looking for that's sufficient. Yeah, there's no ordering necessarily. It might be, but it doesn't have to be. And there's no ability for anybody to predict what this SDR should be.
Okay, yeah, now I understand.
I guess you could predict if I was associating this point right here, which is in between point 1 and point 2, if I associate it with something else over here, some like sense feature, well then this sense feature could predict that's what I'm going to be, right? The sense feature says, oh yeah, you should be at, you know, in some sense, it wouldn't predict these synapses, but it could predict this SDR. A little confusing, but the point is, nobody understands what these bits means. On the dendrite, there's no knowledge. You can't predict them. It's just recognizing it.